I want to thank Dave Hoover for being here to support our webinar and introduce our presenter, Dr. Alfred Hartemink. I'm going to turn the webinar over to you so you can introduce the topic and our presenter.
Thank you, Sean. Hi, folks. This is Dave Hoover, Director here at the National Soil Survey Center. I want to welcome Dr. Alfred Hartemink to our webinar series today. We've been associated with Dr. Hartemink for quite a number of years and have had his benefited from his participation in many of our discussions and investigations. You will hear a slight different accent to his voice, so rather than make you all try to figure out where he's from, he is from the Netherlands. Dr. Hartemink is a professor of soil science and department chair at the University of Wisconsin-Madison. His research focuses on digital soil morphometrics, digital soil mapping, and soil carbon, so many things that all of us are interested in too. He is editor-in-chief of Geoderma Regional and the World Soils Book series. He holds a Master of Science degree in soil science from Wageningen University and obtained his PhD from the University of Reading. Dr. Hartemink will be talking to us today about digital soil morphometrics, which is defined as the application of tools and techniques for measuring, mapping, and quantifying soil profile attributes and deriving continuous depth functions. So he will be talking about various investigations of that, proximal soil sensing techniques, and a number of other topics. So we welcome Dr. Alfred Hartemink. Thank you.
Thank you, Dave. Good afternoon, folks, and good afternoon online. And I'm very honored to be here, and I've been here several times before, and such a powerhouse of American soil science, I should say, and such a wonderful place to visit. Always realizing how much work has been done in Lincoln and throughout the U.S. on soils that I'm very honored to be and humbled to be associated with it and visit today and talk about some of the things that we do at the UW-Madison and the folks I've interacted with over the years. I'll talk about that. So, as the introduction said, it's about digital soil morphometrics. Okay, so the soil pit, like it or not, is at the core of much of what we do, and that was in the First World Congress of Soil Science in 1927 in D.C. here, and some years back we had the Universal Soil Classification meeting in Indiana, and if you look at these pictures. Obviously, a few things have changed. I think there's a slightly better gender balance, for example, only a slightly better, and maybe we have different hats now. But but in a sense, the tools and the instruments and the observational techniques that we had then, some of them are quite similar to what we use today, and quite logically. I mean, a surgeon still uses a pair of scissors, so or maybe they're electrical now, but so that hasn't changed so much. And the main thing is, and that probably will always be with us as long as we do soil science, that we'll have a soil profile wall, and we will look at that wall, and that wall that tells us a story, and that tells us a story about soil genetics, about how the soil is formed, and maybe something about past climates. Well, I don't need to tell to this audience what the importance of that wall is. We will always do that, and we'll. The only thing that we might change is that we say, well, this toolbox, maybe we need to work on that toolbox. So there's been a long search for standardization that started in the 1910s. How we'll look at these soil profiles, how we describe them, and we have the handbooks, of course, and. Simply said, the profile descriptions largely rely on properties that we measure mechanically, and then we visually observe them, and then distinguish horizons, and all of that is known. And then we have some analytical data, sometimes chemical, physical, mineralogical, and then we have thin sections. Are you still doing thin sections here?
Occasionally.
Occasionally, right. But not as much as in the 1980s or 70s, obviously. So, and then we combine all that. Obviously, you have one of the best labs in the world here in terms of soil science. You never hear that in the presidential elections that they say, oh, we have the best soils lab in the world, but I think they should occasionally say that too, that I don't know what candidate should say it, but they should say that we're not only champions in football, but we're also champions in soil analysis. And then we integrated information to understand soils, to distribute how the distribution of soils is across the landscape, and then also for classification purposes. So that's what we do with that profile information. And then these are, let's say, most of the common tools that we'll use, and I think you recognize all of them. Obviously, you recognize the field book. FAO has its own field books, but these are it's a common kit that mostly uses, as you can see, the visible light between 400 and 700 something nanometer. And then here you can see this little stereoscope. I think no one uses a stereoscope anymore, is it? Probably not. Quite wonderful to look through. Students just go in and say, oh, nice. Right, so that's the tools. So in the 1930s, we had already quite a set of what I would call in-situ assessments. And these things are popular nowadays. There's lots of little colorimetric and other tests that people use for instance, in the soil health business or in simple assessment of soil conditions. This one was used for doing soil texture. They had a rapid method. It was from the 1920s. It was a rapid colorimetric method for soil organic matter. Beckman had a portable nitrogen potentiometer that worked reasonably well. And then, of course, many of you know the Helix-Trug soil pH tester, which you had a bit of soil and you added a few things and you colored, and it worked very well. And Truock obviously was from UW-Madison and made a fortune on that little testing kit. And I think that's still being used, I believe. And then Walter Kubiena, I guess well known here, but particularly in Iowa, he had already in the field, he had a microscope in which he, well, this is not a thin section obviously, but in which he did sort of microscopic investigation. So they pinned it in the wall, then he had a battery for the lamp, and that's where the light was, and then he observed these little things. So there was some of this is still being used, some of it is long forgotten, some of it is being reinvented. I think much of the soil health tests that people use nowadays are kind of this level of simplicity, I would say, and some of it is no longer being used and or reinvented. Now, there's lots of other tools and instruments, and as Dave already mentioned, we've grouped that under the term digital soil morphometrics, and some years ago we wrote that introductory paper to it. It's about the application of instruments or tools, techniques for measuring, mapping, and then driving these depth functions. And I will talk about all these three things throughout this presentation. And then the purpose is to enhance our pedological understanding, maybe get some new ideas of how soil horizons should be identified and how soils can be classified. And I should say this is not to replace the old tools. It's in addition. It's a sort of a complementing the existing analytical methods. So there's three parts of it, and I will mostly talk about, I won't say much about this, but we can have a little bit of a discussion on the use and applications. It's about the properties that we can do, and these are common properties that we assess in the field for each horizon. It's about the function, and then about the mapping. So let's first do some quick in-situ assessments, and as Dave already mentioned, it's sometimes named as proximal soil sensing, as opposed to remote sensing, which is from a distance or from a chopper or from a satellite. But proximal soil sensing is what you do in the field. And a handheld XRF here. It works very well. We did it every 5 centimeters for this pit. We did it on other pits as well. It takes 30 to 60 seconds for each observation, so it may be may take you maybe half an hour or so to do the entire wall, and you get the data instantly. If you've got a laptop, you can drive this sort of a function. You can see whether that function tells you something about your horizons. It's a very rapid way of doing it. A bit of a drawback, or not a drawback, bit of a problem is if your soils are too moist, you get a scatter of the X-ray. it doesn't work well if your soils are over 15% moisture or 10% moisture. You can correct for it later when you got the data off the machine, but initially you get too much scatter. You get very good relative values. Absolute values are kind of okay, if you know what I mean. So this was in iron. The iron level was kind of okay. But if you do it for environmental work and you really want to do it for lead, and then you might want to do as well your lab XRF. Another set that we did in a Molik Hapludalf, we get the iron and the calcium titanium, and then we get these sort of weathering ratios or indices that are being used. We knew that from the field, but we also saw that if you look at the calcium levels, that you have a totally different parent material already at that certain depth. So there's things that you'll have confirmed from the things from your observation at the profile well. There's also things that you pick up that you hadn't realized before, and I will talk about that later. So that's on the XRF. Other folks have used the visible NIR. We just bought a tool like this. We'll get that next month. Much faster than the XRF. You get the spectra somewhere between 400 and 2600 nanometers, and you can map very rapidly a range of properties, and they've done it in Australia here for different soils. The nice thing is you have a pistol with this with the instrument, and you just go along the wall, or if you have a soil core in the giddings, you just go along the core. You take the core, or you take the data to the lab, you pull them off, and then you have a bit of work to do with the spectral data to get the values, but it's a fast way of doing it. Another example where they used the visible NIR on soil cores, also worked from Australia. Excuse me, they did a thing called a membership, and they used the spectra then with some sort of clustering technique to derive the horizons from the spectra, as well as compare them to the observations by, let's say, a pedologist. And you can see that the spectra-derived horizons split the A1 in two. This boundary was picked up fairly well. There might be another boundary here that you didn't see, perhaps when you described the soil, but that the spectra suggests there might be another boundary there. So there is ways with these spectra that can teach us something that we didn't know yet, and sometimes we have things confirmed, and sometimes we have things confused. So the second part of it, so this is about properties. The second part is the functions. We all know you have a pit, and this is from Joffe. You have a pit that has maybe 5 or 6 horizons. You sample these horizons, you take them to the lab, and they're being analyzed here. You get the values, and then you can sort of plot these values, and Joffe did that for, I think these are all cations, calcium, magnesium, and then sums of it, and then he sort of plotted them and showed how that changed over. I think we've all done this, and it's a very good way. It suggests that there's a thing called a horizon boundary, and sometimes there are clear horizon boundaries, but sometimes mostly the soil is a continuum. And these boundaries obviously are something that we distinguish, but for many properties they are a continuum. And hence we present them as discontinuous, while in fact they are continuous. It's a bit like soils across the landscape. They're mostly continuous too. And so what people have done is this freehand drawing. So they draw these sort of things, or they have something like an exponential or a regression equation or something polynomial. That can be quite problematic. And a better solution that has been suggested in the 1980s already is this thing called an equal area quadratic spline, shown here. Suppose you have these samples, 1, 2, 3, 4. These are the values, carbon in kilograms per cubic meter. And then you can hand draw the line through this, or you can do something exponential, or you can do the mass-preserving spline. And the mass-preserving spline essentially tells you that I1 and X1 is exactly the same area. So the mass of this depth is preserved the same for the second horizon as well as the third horizon. So what you cut off here, you gain, or the other way around. What you gain here, you cut off here. and what you gain here, you got it there. So this line, which is called spline, and it's an equal area spline, preserves the mass. So at any depth, and for any ranges of depths, you can then calculate any of the values. And it's a very valid way of, let's say, interpolating if you got horizon data. So that's what the spline actually do. That's why it's called equal area. It's quadratic, and it's also mass preserving. So you're not gaining mass. So we've gone from this freehand to a spline with which you can calculate also the uncertainty. So this is the spline data, and then there's some uncertainty with, to something like where we can say we have a continuous measurement across the profile. And that continuous measurement, we can then draw a line for it, because we have essentially measuring points every, whatever, centimeter or half an inch or something similar. Now, a couple of examples here where we did that, and this is a graduate student that works on it. It's the horizontal variation of iron and SOC. So organic carbon for depth. We did this box and whisker plots. We sampled that. I'll talk about this data later, but this is, you can present it as this, you can draw a line through it, or you can spline this data. You can do anything with this data to look at the variation that there is within the depth. I think in terms of horizons, we then inserted the horizons, and you can see how much variation there is within a horizon if you were to sample it separately. And the idea is, Budima Minasni from the University of Sydney, and so we've been working on this over the summer, is that there are a number of what we would call depth functions. And for instance, this is a typical one for carbon. As you know, most of the carbon is concentrated in the top, so you have a sort of an exponential one. This might be a very young soil. You say you look at the clay content or an anti-soil sand or something. This might be what is called a duplex soil, or a soil where you have a very rapid increase in clay. Here there might be a clay one. There might be all sort of forms for these things. And we think that most, if not all, properties have one of these functions. And the functions may be slightly different. This is we're still working on the paper that sort of explains this. The functions might be slightly different, but we cannot think immediately of other functions that are not in here. And most of the functions either increase with depth, or they decrease with depth, or they change gradually or linear, and in what form they can relate. So the next step is that you say, I look at my carbon content. I know it's an exponential function. I look at my iron content. I look at my manganese. I look at my silica over aluminum ratio. I look at my zircon. I look at my titanium. I look at my base saturation, the clay content. You name it. Any property or attribute from the profile probably corresponds with a function or a set of functions. And if you know these functions, you can then say, well, you know, this is a typical function for a young soil, or this is a typical function for an alpha soil, or this is a typical function for the sand in the Nebraska sandhills. Who knows? So that's on the function. So that's the other bit. And then the last bit is probably the bit that we at least that we work mostly on, and that's called what we would call mapping the profile. And you know, we like mapping, and you like mapping too. And we mostly map the soils in the field, but you can also think of the profile wall as a thing that ought to be mapped. You want to map that thing. You say, I'm going to make a map of it. And we've done that in different ways. One of it is that you say you make a raster, and I showed that talk, and then the raster, you take samples of each raster point, and then you can use some sort of interpolated software, just like if you were to raster a field, or you can do a digital image analysis. You get a digital image of your profile, and you do some sort of analysis, or you take a monolith, and you take it to the lab, and you scan that in various ways. This is probably it's a very Wisconsin activity, as you can see. It's very much work in progress. So I think what I'll present here is to be looked at later. So these are two profiles, and this one is from Wisconsin, this one is from the Netherlands, how appropriate. So here we got a bit of loss over outwash, and none of it, it gets very messy in the outwash, as you know already. And this is a spore soil that has a bit of cryoformation in it, so that's problematic. So you can look at these soils in this way. You can make polygons of these soils. So if you do the image analysis, you can say, I'm going to create polygons of these soils. And then if you look at these polygons, and then you look at, for instance, the soil map for Oregon, you see that they're very similar. So the soil profile, to some extent, if you were to map it like this, it's like a polygon map. And that's one way of looking at it. The other way of looking at it is you say, okay, I got these profiles, I rasterize them. So I make a raster of it, and I can increase the cell size, and then I can do all sort of geostatistical analysis on this raster. That's another way of looking at it. So I'll give a few examples now. So we had 3 profiles. I know you like this language. So we had a troxel, and we had a nuclearis, and we had a plain field. So a mollisol, or a patric argiodol, and a typic hapludal, and a typic eudipsamins. So those were the 3 soils that we had. We rasterized them 10 by 10 centimeters, and then we took a sample from the center of each raster, and we took these samples to the lab, and we did a million things on it, and then I show you a bit of results that we have. We learned a lot from these, and this is not the way to do it, but that's what we learned. This might not be the fastest way to do it, but there's much. So one of the things that we did is this is the mollisol, and the mollisol had a buried horizon. It's a bit hard to see perhaps, but here's an AB, a small b, and that comes, of course, up in the carbon map quite nicely. And then there's the iron content. We made these VESPR maps. We have to work on the maps. We are not sure that this is the way to do it, but we will work on it. And the same for the anti-sol. We map the iron and the SOC, and we get these kind of maps. The other thing that we work on, here's the mollisol with the buried A horizon, is that we did some sort of an image analysis. So we extracted from a detailed photograph. We extracted the RGB and in color space, and then we tried to sort of do some sort of an imaging that went nowhere. I should say that was quite difficult. But then we used another color called CIELAB, and where you have 3 coordinates, color always has kind of 3 coordinates. You use the L, the R, and the B, and then you can sort of separate them out, and you get quite good maps that you then can use for segmentation and cluster them, and then perhaps obtain the horizons that way. And we did the same for the anti-sol, and we still work on it to say, well, how do we go from this to some sort of an automated horizon recognition and boundaries? So that's the other step. Pierre Rogier in New Zealand didn't use soil profiles, but he used monoliths. So he took these monoliths that then were taken to the lab, and they had a setup in the lab where they rasterized them, and then they did, I think, an NIR on it, and then they did all sort of regression kriging on the RGB channels again. So they used the RGB space, and then the kriging of the result, and then a segmentation that showed essentially the massive variation within each of the horizons. So these were the 3 profiles. All of them were prevents, if I'm correct, but this one at least was a prevent. So you see this massive variation that occurs within the horizon, and then they work on that segmentation to obtain the horizons. German group led by Markus Steffen in Germany. They have a high resolution visible infrared thing that they also did on soil monoliths of about 50 centimeters, and then they mapped a whole range of properties also to obtain the horizon information and the elemental characterization. So this is the true color, and then they had a classification. They had a carbon map and some sort of an iron form map that they used for obtaining the horizons. So I think I think there is some potential to map this soil profile. The raster sampling is one way. The image analysis is another way, or a monolith scanning. I think a combination of the two are the three, and there is quite a potential to do it faster. I think this is probably the easiest one, but also at least the easiest to obtain the data, but the hardest to obtain the analysis. We might go from there to some more objective horizon identification. When we did the image analysis, we found an E horizon in that molly soil that we hadn't seen while we were in the pit, so to speak. So there is some information in the color coding that only comes out if you do the image analysis. The big thing about the soil profile mapping is that we treat the soil as a continuum, and that we look at the within and the between horizon soil variation. So we very much work on that, so we even what looks like an ordinary A horizon, the variation, if you sample a lot at a short distance at different depths, was quite high for a set of properties. So, in summary, or some summary, so I think all of us agree that we need pattern data, and we need more of them. We have quite a few patterns here, 35,000, or what's the number?
60.
60. Okay, 60,000, I believe. Yeah. So that's a lot, but we need a few more. It's a big country, and we have tools available for every property in soil profile descriptions. We can sample much smaller increments, and we can derive then perhaps these continuous depth functions. There is a potential to map the profile, and with that, because that's maybe the other thing. If we say we know enough about pedology, we are dead and buried. We're done. We don't know enough about pedology. In fact, I think pedology is kind of in the lift and reviving, and we need to increase and enhance our understanding. So here are possibly a couple of tools that we can use, and it's not that they replace the existing methods, but they sort of complement it, and from that we can learn a few things. We have a lot of unresolved issues, but that's why we talk about it. So we had a conference in Madison, and some of you were there. The book is out almost, I believe. I haven't seen it, but I think it's coming out next week or the week after. So that was the inaugural global workshop, and several of you were there. There's another conference next year, combined with the Pedometrics conference in Wageningen. And it's a joint meeting of the IUSS Pedometrics Commission and working groups. So the Digital Soil Mapping Working Group is there, the Digital Soil Morphometrics Working Group is there, the Modeling of Soil and Landscape Evolution, the Proximal Soil Sensors, and the Soil Monitoring folks are there. So that's next year summer, so I think that promises to be a very useful meeting for many of us. And with that, I thank you for your attention.
Alfred, we do have some questions that have come in online. Does the roughness of the pit face affect the results of Vis-NIR?
Yes, it does. And but particularly the moisture content affects it. But the roughness is a big issue, but moisture content even bigger.
Next question, are more horizons transitional than we currently recognize? And they go on to explain that many of our figures show transitions within depth of individual horizons. And do we have sufficient horizon nomenclature to capture that kind of transition?
It's a good question. I suspect we don't. I suspect some of the things that we learn from this is that there is more variation and more language and symbols needed to describe it.
Next question, could soil profile maps be cloned to prepare estimates of 3D soil bodies in the soil landscape for better estimates of soil carbon mass?
Yeah, that would be nice. That would be nice. I don't know what cloning is, but it would be nice. Huh?
Next question, any work comparing what the describer recorded versus what image analysis showed, percent redox features, rock fragments, or maybe boundary thickness?
That would be so nice. Let's say very simple. You have a profile, you have a picture, you analyze the picture, it tells you 70% coarse fragments. You know how we struggle with coarse fragments, we estimate that, isn't it? And sometimes you sieve and then you weigh, and that's another way. But if you can do it based on image analysis, the same for redox feature. What was the other one? There was another example.
Rock fragments, boundary thickness.
Yes, all of that, all of that. So yes.
Any questions from here in the room?
You know, we're measuring or looking at the soil profile as a continuum. It looks to me like you would be not only using different tools that have different types of output. What are your thoughts on managing that kind of data? How would we go about having, what kind of system are we looking at?
I guess before this becomes mainstream, you have an experimental unit that does it, and then so within NRCS, I think that was your question referring to. You can have a unit that says we look at the digital soil morphometrics, and we store our own data, and maybe with time we make it mainstream. But initially we're going to figure it all out how to do it. I would say the questions at this moment are largely scientific, if not technological, particularly maybe technological. How do you do that image analysis of a soil profile? How do you do automated horizon boundaries? How do you do it? So that doesn't mean that we can't do it. It's just that we might not have clear answers yet. And people work on it. I showed that spectral derived horizons that work very well. We work on it. There's lots of, no, not, there's very few, there's quite a few groups that work on it, and they should work on it. And as often with NRCS, you work in collaboration with universities. If things become kind of promising, it finds its way hopefully into the system. So maybe initially with an experimental unit, and then maybe in whoever knows how much time it becomes more standard.
We have a question in the back.
No, it's just an exciting idea. I'm the guy in the soil pit that's always looking at the opposite wall.
Right.
Okay, and saying, well, this wall doesn't look like that wall. And the answer to me is too bad we're looking at this two-dimensional object instead of the, you know, trying to figure out a way to look at it more in 3 dimensions. And it looks like to me something like this soil mapping may be a key, if you will, to be able to somehow map soils in 3 dimensions.
I hope so. Yeah, I agree.
You know,
yeah,
just pure speculation from the back row.
Mm-hmm. I think our field kit has matured, if you like. We've been using it for a long time. It's mature. It's important that we put new tools in it, new instruments in it. These are just some examples. There may be other ones, and there should be other ones perhaps, ones that are maybe smarter or more faster too, in particular. I believe the image analysis is a very exciting bit if you get it working. None of us are specialized in it. We know soils. We don't know ImageJ, which is a software that is very commonly used in image analysis, but we start to learn it. So yeah, I agree.
I guess I have a couple of comments more than questions. One of them is I appreciate your comments about the R&D phase of what we're in, by paraphrasing what you said, in these tools and in these investigations. And I think that's great because we won't know until we wrestle with it. And these tools and the information that we get from them have to evolve, both in terms of what's there, literally what's available from them. And secondly is how do you capture that and information and fold it into some sort of a data structure or convention for actually applying. So it's not just an isolated individual doing it, but that we can, as a soil science community, we can say, okay, these are tools and tactics that really are effective.
Right.
And that is in part, I think we're in the R&D phase and not necessarily the earliest phase of it anymore. but I think it still is, and that's good. And I think when it's kept in that context and with some focus to really push it, develop it, I think there's a lot of promise.
May I make a comment on that?
Sure.
So, you know, of course, I've been in the digital soil mapping community for a while too, or still am. And one thing that we know from digital soil mapping is you need patterns. If you want to do good mapping, you need pattern data. And we are using to the maximum the existing data, but then you arrive at a certain moment and you say we need more data, we need more pits. And we can say, oh, we do it as we've always done it, or we say, no, we're going to do it maybe, I dare not say smarter, but I say maybe faster or more accurate, or maybe using other tools than we've always done it. Just like the surgeon is not using the same tools that he did or she did in the 1950s. So we have different instruments, and we should use them in the pit, or that is I'm very convinced about that. And so. No, Curtis was at the workshop. There were 75 people. I think next year we have maybe 100 people that work on these things, and that's about the maximum. You need about maybe 10 or 15 groups in the world that do little things on it, and that's how you advance a bit, and we learn. And some use the NIR, some use the XRF, some use the image analysis, all of them, and you'll have a few ways, and then perhaps maybe with time we found out that the raster sampling that we did is so laborious. It's a huge job to actually do it, but it's one way of doing it. There's, you know, we have to learn a lot, and science learns a lot by mistakes, I guess. And then we need lots of verification and people that tweak procedures. So, yeah.
The second comment I have is some of the examples that you used were busy profiles, and that's encouraging, because if we use these tools and evaluate fairly simple profiles, that's okay as a starting point, to be sure. But we know that many soils are complicated and don't lend themselves to, in the same way, to any given analysis.
That's true.
And one particular type of soil or morphology that's going to be problematic for these tools is those that have a lot of surface coatings on heads, because they will mask substantially what's going on in the matrix.
Right.
And I don't know what the answer is to get around that, but I'm sure that there's some way that it can be addressed. But it'd be interesting to as time goes by, to take those more challenging profiles and to push and see what are the limits of these tools. Do they work? Can they be made to work? Or are they simply not applicable in some settings?
So you mean the ones that have desert varnish or surface crust?
Yeah, or you know, silt coats or clay films or organic stains or there are carbonates. There are many gypsum. There are many that persist with intensive coatings on particularly pet faces and fracture, but they're quite differently expressed in the interior matrix, and the matrix is a larger volume of the soil.
Right.
So one can be, if you're doing just a superficial scanning and interpretation, you can be very substantially misled by what's really there.
Correct. I agree. Good.
What is your opinion about the future of the polygon? In other words, when, for example, when you teach students about soil mapping, talk about three-dimensional bodies on the land.
Right.
Make an analogy to a lake, for example, is a three-dimensional body. So that you've got boundaries, okay? They seem to be able to grasp that. But if we, with raster, we don't necessarily have to have bodies per se. We can talk more of continua. So do you think that raster perhaps may evolve to a point where polygons, even with the soil horizons, I mean, they're polygons, A horizon, so do you think the polygon has a future?
It's a very philosophical correct question. You say we had polygons first, and we rip it apart and we get rasters, and then from the rasters we may obtain new polygons. Yes. Is that a short answer? And what students need to know is a very different question, I guess. Earlier today I talked to Dave and Richard, and our students need to know They are soil information consumers. They're not producers. They're not go out to the field. They're not classifying soils. They need to see soils. They need to understand soils. They need to understand what you're saying, the three-dimensional body of it. They need to understand raster. But we don't give them data and say, classify this Adjudo, or we're not saying that, but say they need to understand the information and its limitations and all that wonderful information you folks put out there. They need to understand that maybe that soil series is often correct, but sometimes not, because of the density of the information with what it was collected. So they need to understand the limitations of the data and that they consume it, because they won't go out to the field themselves to collect data. They will only consume the information that's already out there. And so they need to know that if the app tells them, or the iPad, we got them all on iPads, tells them this is a troxel, it's a troxel, and we dig a pit or an auger hole, and it only has a 20 centimeters air horizon, then it's not a troxel. And they need to understand why it's not a troxel, because the mapping doesn't include every square foot. So they understand that there's limitations in the information. It's mostly correct, on the county level or on the watershed level, it's quite correct. But if you zoom in behind your house, it might not be exactly as what it says. So they understand that. And then they need to understand that if they use that information, that there's limitations with it in terms of accuracy and whatever. And I think that's what we teach them. And we not teach them, say, go and survey this land. We don't teach them that anymore. Probably you didn't teach them that in New Mexico either, did you?
We could teach them how to ground truth. We couldn't teach them how to map. But we could.
That's the same for us. Because there's no time for it. It costs a full semester to teach them how to do that. Yeah, so we just teach them how to use it, how to consume that information, and understand how it was collected and what the limitations are, which is probably quite enough, hopefully.
Most of my work is in public is exactly that.
Teach them how to use it.
Teach them how to use it and what the limitations are.
Yeah. And then we've done a good job. And then they say it's not good enough. Then they say, well, we can go back to the field, but we need a bit of money.
So a follow-up question to that is, are you teaching these techniques at the undergraduate level? And if not, why?
So there's a difference between teaching and speaking about it. So at the undergraduate level, I speak about it. I speak about these things, but I don't teach them how to do it at the graduate level, or at the 325 level, the pedology class. I actually teach them how to do it. So maybe the answer is that at the introduction soil science courses, you speak about it. At the advanced soil science courses, you teach them how to do it. That's the difference.
And then a couple of comments. Soil profile maps could be managed using space and time, so geocoordinates and Julian date of observation in a GIS system. Just some thoughts. Yeah. And that polygons are just a classification choice for soil information related to precision of this information. Well, Alfred, I want to thank you for your time and effort to make this presentation today, and thanks to all participants for joining in. We had more than 150 people join in today's webinar. The on-demand recording of this webinar will be available on our center's YouTube channel within a couple of days. Feel free to let your colleagues know about this training opportunity. This concludes our webinar presentation.
Thank you.